It's likely that you've seen flux functions before, probably from a finite volume method. But to recap, flux functions describe the flow of some quantity depending upon the quantity itself and possibly other factors, commonly velocity. One of the nice things about numerical flux functions is they permit the insertion of problem-specific knowledge into what would otherwise be an agnostic PDE. So if we know something about the characteristics of that flux, we can use it to properly craft a numerical flux that reflects the physicality of the physical system. So there's many choices for numerical flux functions, some with better properties than others for particular cases, but for our purposes we'll use a very simple flux called an upwind flux. So as the name implies, an upwind flux takes a look upwind of the flow to see what the conserved quantity's value is, and then uses that for our flux. So imagine we have some flow in the positive x direction. We would expect then that whatever we have on just the other side of the element boundary, in terms of a conserved quantity, is what flows in. And likewise, we could imagine if our flow is in the opposite direction, then our conserved quantity on the other side would flow in. So we express this as f hat in place of f for our numerical flux, and it's some function of the conserved quantity on either side of the element boundary. So where q plus indicates the limit as q approaches the element boundary from the positive side, and q minus where the limit as it approaches from the minus element side. So if c is positive, then our conserved quantity on the left side moves to the right, and if our c is negative, then our conserved quantity on the right moves towards the left.